Welcome to week 5. The topic of this week is Dedekind Domains. We're moving on to lecture 24. So just to start things off, we'll start with the definition of a fractional ideal. So the setting is we have a domain A with fraction field K. So we want a generalization of an ideal. So we say that an A module M that's a subset of K is a fractional A ideal and sometimes if it's clear from context I'll just call it a fractional ideal suppressing A. So if it is clear from context we'll simply call them fractional ideal. So the definition is that it's an A module M inside K if there exists an element alpha that's in the ring that's not 0 with the property that the module alpha times M, which is the set of all elements of the form alpha times M in K, such that you vary over little m in the module M. So this new set is an ideal of A. Okay. So in other words, a fractional ideal is inside the fraction field. And so colloquially, in other words, a fractional ideal is isomorphic to an A ideal via this multiplication by alpha. Okay, and this isomorphism is an isomorphism as an A module. Okay, and suppose you have two fractional ideals. So suppose you have two fractional A ideals. So I'll just call it fractional ideals. Then I'll define the product ideal or the product fractional ideal. It's similar to the definition of the product ideal. You consider all finite sums of the form xi, yi in K, such that the xi belongs to M1 and yi belongs to M2. So both M1 and M2 live inside K, so this product, the product is taken inside the field K. Okay, and so we have to verify that this in fact is this definition in fact yields a fractional ideal. So lemma, this definition M1 M2 is a fractional ideal, and so it's not hard to check. So proof, since M1 and M2 are fractional ideals, what does that mean? There exists an alpha 1 that's not 0, that's in A, such that alpha 1 times M1 is an ideal of A, and so call it I1. And there's an alpha 2 in A that's not 0, such that alpha 2 times M2, this is an ideal of A, call it I2. And then you can see that the product alpha 1 times alpha 2, that's not 0, alpha 1 times alpha 2 is in A, This is because since A is a domain, and then if you consider alpha 1, alpha 2 times M1, M2, just play around how where you want to multiply alpha 1 and alpha 2, you write this as alpha 1 M1 times alpha 2 M2. So here we are using the fact that K is commutative. And so alpha 1 times M1, that's what we call the ideal I1. Alpha 2 times M2, that's what we call I2. So this product is nothing but I1 times I2. So we see that when you multiply M1, M2 with the scalar alpha 1, alpha 2, you get the product ideal in A. So this is, in fact, the product ideal in A. And hence is an A ideal. Okay, so this proves the lemma. Now just a few observations. So every A ideal, say I, is in fact a fractional ideal, since we can choose alpha to be 1, and then we just get that alpha times I is just I, and this is an ideal of A. And so in particular, the whole ring A itself is a fractional ideal. And another observation is that if you give me any fractional ideal, say M, and then you try to form the product fractional ideal, M times A, this is nothing but A times M, which is just M. Okay, the fact that M times A equals A times M again just follows since K is commutative. Okay, so here's the definition. So we say that a non-zero fractional ideal M is invertible, or an invertible fractional ideal, if there exists a fractional ideal, say N, such that M times N equals N times M. So this is always true since again K is commutative, but what we want is that the product equals A. Okay, the fact that M times N equals N times M, this is again just true because K is commutative. And so the main requirement for a fractional ideal to be invertible is that M times N equals A, the whole ring. Okay. So one more definition, if I give you a fractional ideal, is there a candidate for an inverse? So given a fractional ideal M, let's define a new module. I'll denote it M inverse to suggestively denote that this could be a candidate for the inverse. So it's all the elements in the fraction field with the property that alpha times x belongs to A, and this is true for all x in M. Okay, so it's just a definition of a set right now. And so the next lemma is that this set is an A module again the proof is just following our nose. So we have to show that it's closed under addition. So suppose you take two elements, alpha 1 and alpha 2 in the set M inverse. What does that mean? By definition, it means that for all little x in M, we have alpha 1 times x is in A and alpha 2 times x is in A. And so to show alpha 1 plus alpha 2 is in the set M inverse, so what do we need to show? We need to show that for all x in M, we have alpha 1 plus alpha 2 times x also belongs to A. But now just observe that alpha 1 plus alpha 2 times x is nothing but alpha 1x plus alpha 2x. But alpha 1x is in A, alpha 2x is in A, and so you're adding two elements in the ring A, so you just get something in A. Okay, so this shows that the set M inverse is closed under addition. And to show that it's closed under scalar multiplication, again it's the same set of tricks. So suppose now we have an element little a in A, and take, say again, alpha 1 in the set. Then what we have is that for all x in M, we have alpha 1 times x belongs to M inverse, belongs to A. And so thus, for all x in M, if we consider A times alpha 1 times x, this is nothing but A multiplied by alpha 1 x. But we've just seen that alpha 1 times x is in the ring A. So this element little a times this element alpha 1 times x, that also has to be in the ring A, because A is closed under, the ring A is closed under multiplication. And so this shows that the set M inverse is closed under scalar multiplication. So we've just shown that the set M inverse is an A module, and this proves the lemma. Okay, and just following similar arguments, it's not hard to show so if you take the product if you take M times M inverse, so again by definition it's all finite sums of the form xi yi, where xi belongs to M and yi belongs to M inverse. And just by the definition of M inverse, we see that this is a subset of A, but because A and M inverse are both A modules, it's not hard to show that this product is in fact an ideal of A. Okay. And so the next proposition, proposition 55. So now the question is, you know that M times M inverse is an ideal of A, and I really wanted, just because I denoted this ideal M inverse, so it suggests that it could be an inverse to M. So I really want this ideal to be the whole of A. It's not always going to be true, but it will be true under a hypothesis. So suppose you know a priori that M is an invertible fractional ideal. then this M inverse is also a fractional ideal. And furthermore, M times M inverse equals M inverse times M equals A. Okay, so if I know that M is an invertible fractional ideal, then the inverse is given by the set M inverse. And so suppose our hypothesis is that M is an invertible fractional ideal. And what that means is that there exists some other fractional ideal n with the property that M times n equals n times M equals A. Okay, so the red box is given to us because by hypothesis M is an invertible fractional ideal. So to prove the proposition, it's enough to show that M inverse equals n. Okay, and so that's what we'll try to prove, that our sets inside K, M inverse and n are the same. Now again, recall that M inverse is all the elements in K such that alpha times x is in A for all x in M. Now suppose you have an element little n in the set n, then again, since we know that M times n equals A, so for all x in M, well, if you take the product x times n, again by definition little x belongs to M, little n belongs to n, so the product belongs to M times n. And again by hypothesis this is A, and so what this means is that little n belongs to M inverse, since if you give me an arbitrary element x in M, n times x belongs to A. Okay, so okay, and so thus we have one inclusion, that n sits inside M inverse. So to complete the proof of the proposition, we want to show the reverse inclusion. So again, so we have seen that M times M inverse sits inside A as an ideal. And so just multiply both sides by n and form the product ideal. So we have n times M inverse sits inside n times A. But now just by associativity, you have n times M close brackets times M inverse sits inside n. But our assumption, our hypothesis is that M is an invertible fractional ideal and n times M equals A. So if we use this hypothesis that n times M equals A, we get that A times M inverse sits inside n, and so this means that M inverse sits inside n. Okay, so we get the reverse inclusion as well. So we have n sits inside M inverse and M inverse sits inside n. And so this means that M inverse equals n, and this completes the proof of the proposition as we have shown that M inverse is a fractional ideal and it satisfies M inverse times M equals M times M inverse equals A. Okay, so what we've shown is that if you knew a priori that your fractional ideal, your non-zero fractional ideal was invertible, then its inverse is given by the set M inverse. And in general, for general rings, not every non-zero fractional ideal is invertible. So we'll work with a very special class of rings where all non-zero ideals, all non-zero fractional ideals will be invertible. So we say that A is a Dedekind domain which satisfies three properties. One is that it's integrally closed. It's Noetherian. And three is that every non-zero prime ideal of A is maximal. Okay. So the next theorem tells us that Dedekind domains are special for the reason I just mentioned earlier. So suppose A is a Dedekind domain, then every non-zero fractional ideal is invertible. Okay. So this is the main result, one of the main results that we want to prove about Dedekind domains, and we'll prove this result over a sequence of lemmas. So we'll prove this result over a sequence of lemmas. So the first lemma is the following. So you take an ideal, a normal ideal or a proper ideal or an ideal in the usual sense, then there exists a product, say P1 up to PR of non-zero prime ideals Pi such that this product sits inside I. Okay, so if you give me any ideal, sort of the first lemma that we want to show is that it contains a product of non-zero prime ideals. So let's assume for the sake of contradiction that this assertion is false. For the sake of contradiction, what does that mean? Then the following set is non-empty. So if you take, so there must be some ideals inside A so that says that I does not contain a product of non-zero prime ideals. So this assertion must be false for at least some, or should be false for some ideal. You take the set sigma of all ideals for which this assertion is false. This set sigma must be non-empty. But since A is Noetherian and this set sigma is non-empty, it must have a maximal element, where I mean maximal under inclusion. There exists a J that is maximal under inclusion. Okay, now clearly J itself cannot be a prime ideal. Because if J was a prime ideal, J contains J. Because since if J is a prime ideal, J would be equal to J, so J contains J. But that's not possible. So this would mean J does not belong to sigma, but by assumption J is an element that's maximal under inclusion. J is an element of sigma. So the only possibility is that J cannot be a prime ideal. And so what does it mean for this ideal J to not be a prime ideal? Then there exist two elements x and y in A such that their product is in J, but x itself doesn't belong to J and y also doesn't belong to J. Okay. And now let's play our trick of forming larger ideals than J. So I'm going to include J and I'm going to include x. So this is the smallest A ideal containing J and x, and similarly you can form Jy, which is J plus y, and again it's the smallest A ideal containing J and y. And now every element of Jx, how does it look like? Is of the form R1 plus S1x, where this first element R1 is in J, the next element S1 is in A. And similarly for Jy, every element of Jy is of the form R2 plus S2y with R2 in J and S2 in A. Now you see that Jx contains J just by construction, but it strictly contains J since x belongs to Jx, but by hypothesis x does not belong to J. And similarly Jy also contains J, but it strictly contains J since y belongs to Jy, but y does not belong to J, again by hypothesis. Okay. So by maximality of J in sigma, now we've got ideals Jx and Jy that are larger than J. So we must have that these ideals that are larger than J cannot belong to sigma, because J is maximal in sigma with respect to inclusion. And so since Jx does not contain sigma and Jy doesn't contain sigma, sigma was the set of all ideals for which did not contain a product of non-zero prime ideals. So if you don't belong to sigma, then you do contain a product of non-zero prime ideals. So this means that there exists non-zero prime ideals, say P1 up to Pn, such that the product P1 up to Pn is contained in Jx, and similarly Q1 up to say Qm says that the product the product Q1 up to Qm sits inside Jy. Okay, but note, so I'll mark these inclusion in red boxes. But note that every element of the product Jx times Jy is of the form this finite sum alpha I beta I, where alpha I is in Jx and beta I is in Jy. But we know that every element of Jx and Jy have this special form R1 plus X Sx, S1x, where R1 belongs to J and S1 belongs to A, and R2 plus S2y, where R2 belongs to J and S2 belongs to A. So using these special forms, so write alpha I as say R1 plus S1x and beta I as R2 plus S2y. So if you just take an arbitrary element of this finite sum, alpha I beta I is of the form R1 plus S1x times R2 plus S2y. And if you just multiply this out, R1, you get R1 R2 plus S1 x R2 plus R1 S2y plus S1 S2 x times y. Now again here R1 and R2 they belong to J, and S1 and S2 they belong to A, and we know that X does not belong to J, we know that Y does not belong to J, but the product XY in fact belongs to J. So we know that the product XY belongs to J. So if you multiply out alpha I beta I, we get R1 times R2. Now both R1 and R2 belong to J. So this product, the product belongs to J. For the second term we see that R2 belongs to J. So the product S1 x R2 that also belongs to J. For the third term we see that R1 belongs to J. So the product again R1 S2 Y belongs to J. And for the fourth term we see that X times Y belongs to J. So the product S1 S2 XY that belongs to J. So you're adding four elements, each of the 4 elements are in J, so the sum also belongs to J. So what we have is that each alpha I beta I is in J, and so that means that this sum has to be in J, and so what that means is that this product ideal Jx Jy is inside J. Thus the product ideal Jx Jy sits inside J. So again, summarizing, we have that Jx contains the product P1 up to Pn, Jy contains the product Q1 up to Qm, and so if you just multiply it out, you get the product P1 up to Pn, Q1 up to Qm is contained in Jx times Jy, but Jx times Jy sits inside J. And so now we have that the product of non-zero prime ideals P1 up to Pn, Q1 up to Qm is contained in J. But this contradicts the fact that J belongs to sigma and hence does not contain a finite product of non-zero prime ideals. Okay. So the only possibility, so our assumption that the assertion is false is incorrect. So our assumption that the set sigma is non-empty is incorrect, and so this completes the proof of the lemma. Okay, so our assertion that sigma is non-empty is not possible, and this completes the proof of the lemma. Okay. So the next lemma that we'll need to prove our main theorem is that every non-zero maximal ideal, let's call it capital P of A, is invertible. So we want to show that every non-zero fractional ideal is invertible, but we'll start by proving that every non-zero maximal ideal is invertible. So proof. So P is an ideal of A, and let me remind you that the set P inverse is the set of all alpha in K such that alpha times X belongs to A. Okay. So now observation, if little x belongs to, so alpha times x is in A, and this is for all x in P. Okay. So if you take an element little x in P and an element little a in A, since P is an ideal of A, it is closed under scalar multiplication. Thus, A times X actually belongs to P as well, and that sits inside A. And so this shows that any element of A in fact belongs to P inverse, so P inverse contains A. So the main claim that allows us, that'll be helpful, so we claim that P inverse strictly contains A. Okay, and so why? So you first choose an element X that's not 0, that's in P. Okay, so this is possible since P is chosen to be a non-zero prime ideal. And again, apply the previous lemma. To the ideal generated by X. So X contains a product of prime ideals. This is a finite product of non-zero prime ideals. But this element little x is in P, so the ideal generated by X is also inside P. Okay. So we know that this ideal X contains a product of prime ideals, some finite product of say R prime ideals. We'll choose R that's minimal. Okay. Now by the prime avoidance lemma, one of the PIs must be contained in P. And say, just without loss of generality, that the first one, so this happens at I equals 1, that is P1 sits inside P. But note that since we have to use a hypothesis that A is a Dedekind domain, and since A is a Dedekind domain, all non-zero prime ideals are maximal. So we have that P1 sits inside P, but P1 must also be maximal because it's a non-zero prime ideal. So thus, the only possibility is that P1 equals P. Okay, so let's mark that along with this series of inclusions. Now, suppose that R equals 1, then what do we get if, suppose this finite product of non-zero prime ideals had R equals 1, so you only had one prime ideal, then what we would have is P1 equals the ideal generated by X, or P1 sits inside the ideal generated by X, which sits inside P, but we've just shown that P1 equals P, so this implies that P1 equals P, but is also the ideal generated by X. So in this case, the inverse is nothing but the A module generated by 1 over X. Okay. So in fact, so in this case, so P1 is invertible with P1 times P1 inverse being A, where the choice of the inverse P1 inverse is given by the A module that's generated by 1 over X. And also note that in this case 1 over X does not belong to A, since X belongs to P, which is a maximal ideal. So in particular, X is not a unit in A, and hence its inverse 1 over X doesn't belong to A. Okay, so in this case, when little r equals 1, and so in this case, when r equals 1, 1 over X is an element that's not in A, but 1 over X belongs to P inverse. And so in this case, we see that P inverse strictly contains A. Okay. Now suppose that this minimal R is in fact larger than or equal to 2. So again, note that P1 up to PR sits inside X, sits inside P, and we have just shown that P1 equals P. Since R is chosen to be minimal, so if you take the product P2 up to PR, this cannot be contained in X, because if it was, we have a product of R minus 1 non-zero prime ideals that's contained in X. Since R is chosen to be minimal, this product P2 up to PR is not contained in X. So let Y be an element of this product such that Y does not belong to the ideal generated by X. Okay, and so what does it mean for Y to not be in the ideal generated by X? So in other words, the ratio Y over X does not belong to A. Okay, so now what do we have? We have that P1, P2 up to PR sits inside X, sits inside P, and we have an element little y that's in P2 up to PR. we also have that P1 equals P, and so thus, so again just rewriting this, this expression out here is just P times P2 up to PR sits inside X, sits inside P. Okay, so in other words, Y times P sits inside X, since Y belongs to P2, P3 all the way up to PR. And so just dividing by X, what do we get? We get that Y over X times P sits inside A. Okay? And so thus this element Y over X belongs to P inverse, since Y over X times P sits inside A. So we've constructed an element Y over X that belongs to P inverse, but this element Y over X does not belong to A, and so this proves the claim that P inverse strictly contains A when R equals 2. We've already shown this claim when R equals 1. Okay. So now to complete the proof of the lemma, now observe that P times P inverse, this product, is an ideal of A. Now what we have is that P inverse is contained in A, and so firstly multiplying both sides by P and then forming the product ideal, we get P times P inverse contains P times A, which implies that P times P inverse contains P. Okay. So now what do we have? We have that P times P inverse is an ideal of A and it contains P, but remember that P, so since A is a Dedekind domain, P is a maximal ideal in A. So the only possibilities are this product has to be P or this product has to be A. So we want to show that P is invertible, so it's enough to show that the second possibility occurs. So to prove, to complete the proof of the lemma, we need to exclude the possibility that P times P inverse equals P. Okay, so this is where we'll use the hypothesis that A is integrally closed. So again, since A is Noetherian, every ideal is finitely generated, so P is a finitely generated A module. Now we have this element Y over X which belongs to P inverse, but Y over X does not belong to A. Now if P times P inverse was equal to P, what that tells us is that Y over X times P still sits inside P. And so thus, using the characterization of integral elements, so this goes back to proposition 1, and this was his characterization in 3 of proposition 1. Since P is a finitely generated A module and y over x times P sits inside P, we have that y over x is integral over A. But since A is integrally closed, what this means is that, well, y over x belongs to A itself, but again this contradicts our hypothesis that y over x was an element that doesn't belong to A. So the only possibility, so we've excluded the possibility that P times P inverse is P, so the only possibility now is that P times P inverse is A. So this excludes, this is not possible, and excludes the possibility that P times P inverse is P. So the only possibility is P times P inverse equals A, and so this shows that the non-zero prime ideal, which is also maximal. So in a Dedekind domain, every non-zero prime ideal is maximal, and every maximal ideal is of this form. So this shows that the non-zero prime ideal P is invertible. Okay, so this completes the proof of the lemma. Okay, so in the next class we'll complete the proof of the theorem that every non-zero fractional ideal of a Dedekind domain is invertible. Thank you.